This episode was brought to you by CuriosityStream, plus Nebula. Hey everyone, it's Inés, and look, I found a snail. Do Mik Scheper. I happened upon them as I was crossing the road in the rain, and my foot very narrowly missed their big shell. So concerned, I decided to pick it up to save it from the perils of crawling by a rainy main road, and I was also curious to see how its size would compare to the giant African land snail. It's Aschatina folica. Yes, that's the giant African land snail. And yes, I know they're invasive, but they have grown on me, literally and figuratively. How could you resist the cute eyes of this cabbage-chomping machine? And speaking of their cute eyes, truth be told, I have often wondered how well Scheper actually sees what the world is like for a tiny, or in this case, rather large snail. Truth be told, mollusks are some of the most interesting animals out there as far as eye evolution is concerned. Although the human eye can seem mind-bogglingly complex on the surface, with the retina, the cornea, the lens, how such an organ evolved from scratch is actually pretty decently understood, and it has happened convergently on multiple occasions. And many different mollusks actually represent quite a few of those intermediate steps. Firstly, a small layer of pigmented cells connected to nerve fibers appear. These are photoreceptors, as they are sensitive to light and allow the organism to perceive light and darkness. With time, this layer of photoreceptors becomes larger, and the surface begins to invaginate, allowing the pigment cup eye to discern directionality from the light. With time, the invagination deepens, forming an optic cup or pinhole lens. The small opening allows light to be focused well, allowing for basic shapes to be discerned, but with the caveat that it is prone to infection given that the interior of the optic cup is in contact with the water from the outside, and also that it doesn't really perform well in low light environments because the pinhole doesn't actually let through that much light. However, such a small opening does mean that the growth of a transparent epithelial layer over it is a very easy adaptation to evolve, and this allows the separation of the interior of the eye from the outside. From here, it's a lot easier for the eye to develop its own more fine-tuned adaptations, such as vitreous humour that refracts the light more optimally than water, a contractible pupil to control the amount of light that enters, a lens that will focus the light, specializations in the retina, and so on. And as said, across the mollusks, and to a lesser degree within the gastropods, different species represent different steps across this spectrum. And in this case, Scheper actually places around here, as snails do have a closed eye cup with a cornea and a very basic lens. However, despite their large eye stalks and careful eyeballing of the world around them, land snails actually don't see that well, and they don't rely on their eyesight as their primary sense. If you've ever picked up a snail, you've probably noticed that unless they've slowly and carefully placed their eye in front of an object and then avoided it, they more often than not bump their eye stalks into objects around them. Their retinas are quite shallow compared to species of marine snails which are known to see substantially better, suggesting that terrestrial snails probably aren't using their eyes to recognize objects because they can't focus them as well, but instead they might be measuring light intensity at large to get a sense of their surroundings. Nonetheless, despite their vision seeming quite unfocused, their eyes do in fact have some very interesting features that you may not have known about. Firstly, each tentacle-bearing eye capsule doesn't actually contain one, but two eyes, the main eye and the accessory eye. They both share the same cornea and optic nerve, but they have separate lenses and separate ultrastructures. That being said, you probably wouldn't be able to see the two eyes easily with a naked eye, given that the main eye is only about 1/8 of the size of a pinhead, and the accessory eye is 1/5 to 1/3 of the size of the main eye. Initially, the function of the accessory eye was not quite clear. It was hypothesized to be sensitive to infrared light, even though snails in fact do not respond to stimuli with a wavelength longer than 750 nanometers. And interestingly, although the main and accessory eye both have the same two types of photoreceptors in similar concentrations, the accessory eye lacks what is known as a screening pigment, a layer of pigment that is behind the retina, which absorbs light and allows for image formation, meaning it would be unlikely enhancing an image in any way, given that the lack of screening pigment means the accessory eye will detect light from any direction. However, when the eye is retracted within the tentacle, the accessory eye may be the perfect way to detect the changes in light intensity levels at large and alert the snail to find out what's going on. Although not all terrestrial snails have accessory eyes, some species of slugs and annelids have convergently evolved similar structures. Secondly, snails are achromatic, which means they are not able to perceive colour. Now, you may have just overheard me saying that snails have 2 photoreceptor types, and might have thought that this means that they could perceive colour. After all, we have 3 cone types, and each one has a different peak spectral sensitivity that peaks at red, green, and blue. This means that the same wavelength of light stimulates each cone type differently, and our brain does the wonderful job of integrating those different signals into what we perceive as colour. But despite snails having 2 types of photoreceptor, the spectral sensitivity is the same in each one, meaning that they won't be useful in detecting colour. They do, however, react differently to light. One type of photoreceptor increases its firing rate with more light intensity, and they decrease it when it is reduced. So in essence, they depolarize in response to light, whereas the other type of photoreceptor does the opposite. It hyperpolarizes in response to light and depolarizes in darkness. So the former could be called lightness neurons and the latter darkness neurons. Now, different photoreceptor types that depolarize and hyperpolarize in response to light and dark are not unique to snails, but in the absence of photoreceptors that allow colour detection, the system allows them both to be able to distinguish different light intensities quite precisely and to be capable of light detection in both light and dark environments, as the darkness cells will be able to dark adapt and allow the snail to see in a low light environment. Although snails aren't thought to rely on eyesight for finding food, they are capable of learning and recognizing different patterns. They also use light to orient themselves, and they are known to seek out the darkest location in their environment, presumably to avoid being eaten by predators and not drying out. However, seeking out dark environments doesn't mean they are merely avoiding light, but they're actually using their enhanced ability to detect relative light intensities to scout out and move towards that dark spot, even if it actually means that they have to cross through a brighter section temporarily. And finally, snails have the most extravagant blink of the animal kingdom, capable of pulling back their eye capsule into their retractable tentacles to protect them from harm. That being said, in the unfortunate event that harm should come to their eyes, their final superpower is their ability to regenerate them. Should a giant African land snail lose its eye, it will be able to grow back the tentacle and its eye over the course of a few weeks or months. Young snails are able to repair the damage faster, whereas older snails that have ceased growing generally take a lot longer to restore their eye and their tentacle, and they actually don't always recover their vision entirely. Some of their behaviour that is triggered by vision, such as reacting to changes in light and scoping out those darker nooks and crannies in their environment, is occasionally compromised in older individuals, suggesting that even if the eye structures regenerate, the optic nerve connecting them to the cerebral ganglion may not retain the same regenerative capacity, and the point at which this switch happens in snails is certainly very interesting from the perspective of regeneration and ageing. So overall, snails do a pretty good job with what they have, even if they can't see very well. Whilst their eyesight might make it harder for them to enjoy today's sponsor, your eyesight certainly won't. CuriosityStream is the first streaming platform devoted specifically to feeding people's quest to learn, explore, and investigate more about the world, and they offer thousands of documentary and non-fiction titles to their users. And you can enjoy 1 month for free on me by going to curiositystream.com/drawcuriosity. If this video has piqued your interest in animal vision and you want to see more, I can recommend the title What Animals See to learn more about precisely that from the mouth of Professor Thomas Cronin, who incidentally is easily one of the leading experts in mantis shrimp vision. A CuriosityStream subscription also includes a free Nebula subscription, enabling you to view and support more of your favourite educational creators with none of those pesky YouTube adverts. And that looks like it's pretty much all for today. As always, thank you so much for my wonderful patrons on Patreon for supporting Draw Curiosity. And as always, thank you so much for watching me, and I'll see you in the next one.